So we're going to talk a little bit now about how to solve initial value problems. Recall that an initial value problem is a differential equation combined with initial conditions. Okay, so how do we solve an initial value problem? Well, of course, the first thing we can do is write down the general form of the solution to the differential equation, and there it is. Now, there's, of course, some work to be done there. You have to write down the characteristic polynomial, find the roots, etc. Okay. All right, so there is the general solution. Now, that also allows us to deduce not only what y is in general, but what y prime and y double prime are. And we're going to need that to take advantage of these initial conditions. So specifically, what these initial conditions say is that when x is equal to 3, y prime, and y double prime are equal to these values. So those values go here. We plug in x equals to 3 in all of these appropriate positions, and the result then is this system of equations. And all we have to do then is solve for C1, C2, and C3. And once I know C1, C2, and C3, then I know the solution that I'm looking for that not only solves the differential equation but also satisfies these initial conditions. Okay, and that's all there is to it. Except for the fact that this is not a pleasant system to face up to solving. And look at these coefficients. Terrible. Like these numbers. Sine of 3, that's not a convenient number to work with. That's a transcendental number. We don't know how to write that down. And row reducing this system with all of these nasty numbers in there, very inconvenient. Even if we could do it, what we would be left with is a solution expressed in terms of coefficients that were bearishly difficult to write down. Okay. So this is an undesirable strategy in this case. So we're going to make a trick move. And that is, we're going to do a substitution. We're going to make up a new variable called t, that is x minus 3. And we're going to rewrite the differential equation. We're going to rewrite the initial conditions, all in terms of t instead of x. So the differential equation, at a glance, appears not to have changed. You'll notice that looks exactly like the differential equation that we just got through looking at. So what happened? Well, what happened is, here we're writing down derivatives in terms of t. These are derivatives with respect to t, as opposed to derivatives with respect to x. And it just happens to be that derivatives with respect to x are equal to derivatives with respect to t because dx dt is equal to 1. So by way of the chain rule, same thing. Okay, so the differential equation looks exactly the same. Just keep in mind that these are t derivatives, not x derivatives. Okay. The initial conditions look different. This is because when, if you look back up here, our given initial conditions, the initial conditions are given when x is equal to 3. Well, here's the thing. If x is equal to 3, x is equal to 3, then t is equal to 3 minus 3 equals 0. So when x is equal to 3, t is equal to 0. With that in mind, this actually says exactly the same thing as the initial conditions that we started with. They look different because these are values of t that we're putting in here instead of values of x. But of course, these y's over here are thought of as functions of t, and so the conditions that we put in have to be in terms of t. So it looks like the conditions are different, and algebraically, I suppose that they do look a little bit different. But these represent the same actual initial conditions. Okay. All right. Now, with that in mind, how would we solve this initial value problem? And is this any easier than it had been? At a glance, not clear that it is. We can write down the solutions to the differential equation. There's the general solution. Take various derivatives, just as on the previous page. And we know that for these values of t. For this value of t equals 0, we know that y prime, and y double prime take these values. And the good news is, note that the value that we're plugging in here for t simply algebraically an easier value. We're plugging in t equals 0 into these functions here as opposed to x equals 3. And 0 is just a more convenient number for these functions. Specifically, e to the power of 0, no problem. Right? That's just 1. Cosine of 0, no problem. That's just 1. Sine of 0, no problem. That's just 0. So the algebra works out to be much more convenient. And look at how the system turns out. System turns out to be this. So solving for these coefficients that you'll note I'm calling D1, D2, D3, those coefficients, not that bad. This algebra here, sure you have to do a row reduction, but it's a row reduction that's going to involve rational numbers, nice, convenient rational numbers. Okay. And, of course, once you know the D's, once you know what these D's are, D1, D2, D3, that means that you know the solution that satisfies the differential equation and the initial condition. Okay, now there is one last little thing, and that is that we have our solution written in terms of t. Our question was not written in terms of t. Our question was given in terms of x. The input variable was x. The starting value of x is 3. So I need to have a solution written in terms of x. And I don't. Here I have a solution that's written in terms of t. Good news. That's easily dealt with because t is just x minus 3. So you just plug that in. And then you have your function in terms of x. All right. So the thing that makes this work, the thing that makes this trick work is this idea that what we're effectively doing is finding a different basis to work with. I mean, algebraically, it's a substitution. We find a substitution that makes the arithmetic easier. But from a more sophisticated point of view, we started looking at this initial value problem in an unintentionally an awkward way. We're looking for a particular solution of some sort in terms of this basis, these three functions. And the reality is that in this instance, this function just isn't a very convenient linear combination of these basis vectors. Said differently, we've got a bad basis here. This is an unfortunate choice of a basis. Now, it's the convenient basis to write down, but that doesn't mean that it's the convenient basis to use. And we found here that it was a very inconvenient basis to use. And look at the nasty algebra that we would have to slog through in order to use it. So, importantly, when you make this substitution, what you're really doing is saying, I would like to express the function I'm interested in terms of a different basis. We're just choosing a different basis. We're choosing these three functions instead of the three functions on the previous page. Now again, they look similar, but they aren't. This is not e to the negative x. It's e to the negative t, which, once you plug back in, is e to the negative x plus 3. It's a different function. Likewise, plug in here, t is equal to x minus 3. That's a different function than what we were looking at on the previous page. So conceptually, algebraically, what's going on is that this substitution makes the algebra a little bit easier. Conceptually, this substitution does a change of basis. And as it turns out, this basis is just much more naturally suited for understanding the function that we're actually interested in than the basis on the previous page.